Hi everyone, welcome to this video, and today we'll be talking about Thevenin's theory and its application in simplifying the complicated circuits. So let's dive quickly into this theory of the Thevenin and to see that how it can be really applied to the circuit. So essentially, Thevenin's theory states that every linear two-dimensional circuit or two-terminal circuit can be replaced by an equivalent circuit, as you can see here on this screen, with a series combination of a voltage source and a resistor. So we can summarize a complicated circuit that can have many branches and nodes into a simplified version of it that has only one voltage source and one resistor. And then we can make use of that and connect it to any other arbitrary load or the other part of the circuit to analyze the rest of the circuit later. So that just helps us to find out the response much faster and easier. And we'll see in the upcoming examples. In this process, we will need to break it down into two pieces. First, we need to find out what is the voltage of the Thevenin equivalent circuit. In that case, that will be simply the open circuit voltage, which means that we would keep all of the current sources and voltage sources of the initial circuit, and we just need to find out what is the open voltage open circuit voltage across the terminal of interest. So that will be simply finding out what is the voltage. However, for the resistance, the equivalent resistance, we need to zero out all of the sources. And the zeroing out of the sources was something that we discussed in the superposition video in the previous one. And we just need to find out what would be the equivalent resistance seen from the terminals of interest. So essentially, if you want to find out the resistance seen from A and B terminal, we would connect a voltage source, an arbitrary voltage source over here. We would call that as, for instance, V. And we would need to find out what is the current that is exiting that node with this polarity of the voltage source and with this direction of the current. So that would feed all of the circuit that right now has no independent sources. And this is only a resistive source in this case. So this voltage is going to drive this whole resistive circuit with this amount of current. So in order to find out what is the amount of the internal resistance, it's simply Ohm's law by dividing V over I. So Rn is simply V divided by I. And in that case, we can simplify the circuit by just finding out, assuming that V is, for instance, 1 volt. That will be just for simplification. But if you don't do that, that would not make the whole solution different. So we'll see how this company, so we'll see how combination of this Thevenin voltage and independent resistance can help us simplify complicated circuits in the next few examples. Okay, so over here is the first example that the question is asking: find the Thevenin equivalent terminals at the terminals of AB, or essentially here of the circuit. In order to find the Thevenin equivalent, so we need to find out the Thevenin voltage as well as the resistance. So V Thevenin and Rn that is seen from these two terminals. For the Thevenin voltage, that would be simpler to discuss because that's simply the open circuit voltage. It's essentially the same circuit that we see, but we just need to find out the voltage across these two nodes so where there's no connection between them. It's essentially just solving the whole circuit at the moment. So now we have a single loop essentially because A and B are open circuited. So we can make use of a KVL on this loop with this direction as I'm pointing out. So in the clockwise direction for VAB, we can use KVL in the clockwise direction. And for that, we can start from this bottom reference point and try to move clockwise through this 70 volts. So that would be minus 70 because we're entering through the negative input, and then plus VO, that would be the voltage that we don't know what that is, um, plus. So the current that we are talking about is essentially I that is passing through all of the components. And in that case, if you want to find out what's the voltage drop across 20 kilo ohms, that would be simply 20 times I. So 20 times I. Then we are entering from the positive node, positive end of this voltage source, that would be plus 4 VO equals 0. However, we need to be mindful that there is an internal relationship between VO and I, simply because VO is the voltage drop across this 10K, and that is nothing but 10K times I. So VO equals 10 times I. So in that case, we can further simplify that by minus 70 plus 10I plus 20I plus 4VO, which VO again is 10I, so 4 times 10I equals 0. So we can simply solve for I in this case. 40 into 20 into 10, that would be 70. So 70I equals 70 because that would go to the other side of the equation. So essentially I equals 1. Therefore, if we have I of 1, we can then find out what is the voltage difference between A and B. Simply, we can assume that here is the open circuit. So we can reuse the KVL, but this time on a different through different loop. In this case, we'll be using that through here, for instance. So I would start from this bottom, which is the 0, and enter from the negative of the open circuit. So the open circuit minus sign plus 20 times I plus 4 times VO, which in this case it's 10I equals 0. So that is how we can start from here and move into minus V open circuit plus 20 times I plus 4 VO and get to 0. And in this case, we know what is the value of I in this case. I can simply write down V open circuit is 20 plus 40, that will be 60I. And since I is 1, so that will be 60. So this is the open circuit that we have for the Thevenin voltage indeed. Part of the analysis is done, then move forward in finding out what is the equivalent resistance, or Rin. For Rin, we need to take a look at the circuit from a fictitious voltage source. However, we need to nullify all of the independent voltage sources. For instance, in this case, this voltage source is going to be short-circuited. We won't actually, we won't be working on this dependent voltage source, by the way. We would only nullify this independent voltage source. So let's try to simplify the circuit in that sense. So I would say what would be the fictitious voltage source over here as the value of 1 volt, for instance. And I'm trying to find out what is the current that is passing through that, so I, and that is going to be through this 20K as well as this independent voltage source for VO. On the left side, I have this 10K, and this short voltage source is automatically going to be short-circuited. And VO is again the voltage drop across this resistor. Trying to find this I helps me find out what is the resistance seen from these two terminals, essentially, because if this is the voltage source of 1 divided by this resistor, by this current I, that would give me the effective resistance seen by this voltage source. So that would be the resistance, equivalent Thevenin resistance indeed. So the only part of this question is simply find what the I is. So in order to do that, we would consider that I is going up. Um, and that helps us to make use of a KCL at this node. We just then need to find out what is the currents on all the other branches. For instance, what is the current passing through this resistor? We already know the voltage drop across that VO from the left to the right helps to get to the current of VO divided by 10K. That is flowing to the right side because of the polarity of positive polarity of the voltage source. So essentially, I would write that down as VO divided by 10K. So that is part of the currents. So in that case, we have two currents, VO divided by 10 and I, that are entering this node. And obviously, the exiting node is simply the summation of these two. So that would be the current to the right side. That would be I plus VO divided by 10. We can make use of a KVL in our structure such that it incorporates all of the paths of, for instance, this path or even this path. But it would be easier for us to engage this path, for instance. So let's try to focus on this branch for the KVL. So for that, I would start from the bottom uh, as the reference point and enter 1 ohm, 1 volt from the negative input. So that would be simply -1 from 20K. So from the 20K on the right side, it's going to a current of I plus VO divided by 10 is going to pass through 20K. So 20 times I plus VO divided by 10. Then I hit an independent voltage source plus 4VO, which equals 0. So that is my first equation, that I have two unknown variables of I and VO, indeed. So I need to find another equation that relates these two together. So if I look closely at this question, I can see that on these two terminals A and B, the voltage drop across them is 1 volt because we put that fictitious voltage source. However, on the other hand, it equates with minus VO here as well, because minus side of the VO is to the top and positive side is to the ground. So essentially, 1 volt equals minus VO. So that would be the second equation, VO equals minus 1. So we can now resolve this question by just solving that for I in the first equation. So that would be -1 plus 20 times I plus, so instead of VO, we would have -1, so -1/10, plus, again, VO, that would be -1, that would be -4 equals 0. Now, we can then simplify that with -1 plus 20I minus 2 minus 4 equals 0. Then I can solve for I. It would be 20I equals 4 and 2 and 1 would be 7. That can go to the other side of the equation, which would help me find I equals 7 divided by 20. Now that I could find what is the current passing through this fictitious voltage source, I need to just make use of the equation of R Thevenin is equal to that 1 volt of voltage source divided by I. And in that case, it's essentially 1 divided by 7/20, which is 20 divided by 7 ohms. So remember that it would be K indeed. So remember that we now have the resistor and the the voltage with respect to this Thevenin equivalent circuit. If I want to simplify the circuit, it would be something as follows. The voltage source would be 60 and the resistance would be 20 divided by 7K. That would be the equivalent Thevenin from that is seen from the terminals A and B. Okay, so here is another example that is asking find the Thevenin equivalent circuit to the left of RL. So right now we are having a two loop circuit that has only one independent voltage source. We would be simplifying the circuit again, simply with breaking it down into two pieces of finding out what is the open circuit voltage seen from across this RL, and that would be our voltage Thevenin or open circuit voltage Thevenin. Then we would move forward with replacing this RL with a fictitious voltage source and finding out what is the current that is exiting that in division of them. That would give us the resistance of the circuit, knowing that we would then try to nullify all of the independent sources in the circuit. So let's try to find out what is the open circuit voltage in the first place. So I'm going to actually simplify the circuit in this case. So 9 and 2 Vx is across that. 1, 3 Vx. And we have this 4 ohms. Other than that, we don't have anything across this end that we would like to find the V open circuit, which is the V Thevenin of the equivalent circuit. So in order to find that, we didn't nullify any one of the independent or dependent sources. We just need to find out the open circuit voltage. We just need to just solve for this circuit in this case. Remember that when we have this open circuit on this end, it means that there's no current flow through this 4 ohms. It essentially means that there's no voltage drop across this. So the voltage at this node is equal with the voltage at this node. So essentially, we can actually simplify the circuit by just looking at this a single loop over here. So once we do that, we're dealing with only a single loop that we can easily make use of a single KVL in this loop. If I want to make use of a KVL, I can use simply a clockwise direction with the ground at the bottom, and starting from the bottom, the KVL is -9 plus Vx plus so the current that is passing through the elements is I. And in this case, when I is going to pass through here, it would pass through this 1 ohm resistor as well. That will be 1 times I plus 3 Vx equals 0. On the other hand, we also know that since I is passing through this 2 ohms, Vx is equal to 2 times I. So Vx equals 2I. So if we combine these two, and if I replace Vx in the first equation with respect to the second equation, I can simplify this as -9 plus 2I plus I plus 3 times 2I equals 0. So that would be 6 plus 1, 7 plus 2, 9. I equals 9. And essentially, in this case, I equals 1. When I equals 1, then I can easily find out what is Vx, which is 2 as well. Now, we need to know what is the open circuit voltage. So the open circuit voltage is simply considering a combination of 1 and 3 Vx. So starting from the top to the bottom, it would be 1. So the voltage source of the open source is 1 times I plus 3 Vx. And we know actually both of them. I is 1 plus 3 times Vx, which is 2. Essentially, that gives us 7 as the 7-volt open source voltage. So that would be the V Thevenin of this structure. So let's move on and try to find out what is the resistance, the equivalent resistance seen from the across this RL. So we need to first nullify all of the independent sources. In this case, this voltage source is going to turn into a short circuit, and replace this RL with an fictitious voltage source. And let's simplify that at the bottom. So if I put a voltage source over there with a value of 1, for instance, instead of RL, 4 ohms, 1 ohm, and then we have this independent voltage source that we need to keep that 3Vx. Then we have 2 ohms, Vx is across that. Then we have this short circuited voltage source that I just need to find out what is the current that is passing through this one um, voltage source, the fictitious voltage source. So I is passing through that. So 1 divided by I will take me to the equivalent resistance. Now I just need to solve this equation in this parallel combination of the branches, and to try to figure out what the value of I is. So I can make use of KCL at this node. I know that the entering current for this from the right side is I. I need to figure out what are the exiting currents from this node. So I know that the voltage drop across this 2 ohm resistor is Vx. So I can easily find out the current passing through that as Vx divided by 2. So I would just write it down as the current is going to be Vx divided by 2. So the summation of these two currents of I and Vx over 2 is going to pass through this middle branch, obviously. So I'm going to actually write it down as I plus Vx divided by 2. So essentially, we have used KCL automatically at this node, and tried and figured out all of the currents passing through all of the branches. Now is the time to make use of a KVL. And a KVL can be used on, for instance, um, this branch that the first this loop that I'm highlighting that. So that would be something that I would be using. So I'm highlighting that to make it clear that which loop I'll be using KVL. And for that, so KVL, starting from the reference point and moving up according to I'm entering the negative side of this 1 volt. So that will be -1 plus 4 times I. So 4 times the current passing through that, plus the current passing through this 1 ohm is simply I plus Vx over 2. I plus Vx over 2. Then I have this dependent voltage source as 3Vx. So plus 3Vx equals 0, because we came back to our initial position. So this is one of the equations that we have, but obviously we have 2 unknown variables over here. We just need to add a secondary equation so that we could resolve this question. So the second equation in this case can be with respect to the condition that we have here on the left side. So we can also make use of another KVL, and this time the KVL can be through this larger loop. So the larger loop that I'm highlighting is essentially this one, because that has simpler terms for me to use. So the KVL, let me just highlight actually the first KVL that it was on this yellow line. And the second KVL, it's going to be on the green path. So essentially, starting again from this bottom and moving up through this resistor's through this voltage source, that would be again -1 plus 4i minus 1 plus 4i. Then we hit to this point, which we have minus Vx, and then we get to the ground. Minus Vx equals to 0. So that will be our second equation that we need to consider. So essentially, if we compare uh, these two equations, we can see that if we subtract them, these two first components are going to cancel each out. And this minus this would give us some information. So let's try to label them as equation 1 and equation 2. So if we subtract equation 1 and 2 from each other, that would be equal to, so I plus Vx over 2 plus 3Vx from the equation 1 minus from equation 2, that would be minus Vx equals 0. Remember that these two terms are already zeroed out because they are very identical. Now, if I simplify that, so this would be plus Vx and 4Vx with the summation of them. So that will be I plus Vx, that will be factored out, 1 over 2 plus 3 plus 1. So this would be 7 over 2, essentially. 7 over 2 Vx plus I equals 0. That means that I is equal to minus 7 over 2 Vx. So, or essentially, I can simply write what is Vx indeed. Vx is minus 2 over 7 times I, because essentially I would want to get to the value of I at the very end. So now that I have the Vx in terms of I can replace that in equation 2 and simplify that. So equation 2, let's replace Vx in equation 2. That will be minus 1 plus 4i minus Vx is minus 2i divided by 7 equals 0. So this way I can find out what is I, which in this case it would be minus 1 plus I times 4 plus 2 over 7 equals 0. So I essentially is going to be, this is going to be 30 divided by 7. So I would be minus 7 divided by 30. That's the value of I. No, plus 70 divided. So essentially I would be equal to 7 divided by 30. From this equation, I equals 7 divided by 30. And essentially, once I is known, we can find out what is the R Thevenin is known, because R Thevenin is simply the inversion of 1 over I, which in this case is simply 30 divided by 7. So I'm going to actually highlight that as well. That's how we could simply write it down, a Thevenin resistance and a Thevenin voltage that equates this complicated circuit when we are looking from to the left of this RL. So 30 divided by 7 is the resistance, the equivalent resistance, and 7 volt is the Thevenin voltage. So The next part of the question is simply determine the value of RL that will draw the maximum power from the rest of the circuit. So I'm going to actually simplify the answers in the previous part here. So this is a simplified model of the equivalent circuit of the Thevenin equivalent circuit of this circuit that is coupled with this RL. Now, if you want to find out what is the maximum power that is being transferred to this RL in the simplified circuit, we know that the resistance RL should be equal with the source resistance. So in that case, RL has to be equal to 30 divided by 7 ohms. That would be the ideal case for maximum power transfer. So that would be equivalent to impedance matching, which means that the impedance of the load equals with the impedance of the source. So once that's done, we need to then figure out what is the power in this case that is passing through that. So imagine that we are dealing with a voltage source of V. The power that is being delivered to two loads of value of RL would be simply V squared divided by 4RL. And that can be calculated simply by knowing that if this is the voltage source V and we have two resistors RL, so essentially the current that is entering this branch is simply V divided by 2RL. So that's the current. Now the power is simply multiplying that current by this by itself, and so the power is simply RL times I squared, and RL times I would be V squared divided by 4 RL squared. And if you simplify that, that would be V squared divided by 4 RL. And that's what we are actually using that here. Now that we know what is the voltage, that will be 7 to the power of 2 divided by 4 times 30 divided by 7. That needs to be simplified, and the final answer in this case is going to be 2.9 milliwatts. So that is the total maximum power that can be delivered to the load, equals P max. So now that we have found a way to make use of Thevenin's equivalent circuit in simplifying complicated circuits, here is an example that I'm leaving it as an exercise to you guys to find out the value of R in this circuit that needs the maximum power transfer to this 10 ohm resistors. So essentially, that's not complicated. Just need to figure out a way that what is the equivalent resistance seen from these two nodes of, say, A and B. That simplifies the whole circuit around them. And then if we want to make sure that the whole circuit is going to get the maximum power being delivered to this 10 ohm, so we need to find out the voltage resistance. So that's not that much complicated compared to the previous examples. We just need to again assume that this 10 ohm is the resistance RL, and we need to find out what is the equivalent to Thevenin circuit across this resistor to find out the resistance of the Thevenin, and that resistance should be equal to 10 ohms in order to impedance match the circuit with respect to this load. That's how we would make use of the Thevenin equivalent circuit over here. Then once the Thevenin equivalent resistance is calculated with respect to this R, we can easily equate that with 10 and find out what is the value of R. Once that's done, the second part of the question is simply the maximum power transfer that we just calculated in the previous example. Thank you for watching. Hit like and subscribe to the channel if you enjoyed this video.